In this presentation, we discuss equipment grounding. Equipment grounding is required for all photovoltaic systems. All exposed metal parts in PV systems must be connected to ground. Grounding supplies some amount of protection from lightning, but the main reason for grounding is to provide partial protection from electrical shocks to anyone who touches an exposed metal part, whether intentionally or unintentionally. Because you never know who's going to wind up touching the exposed metal of your PV system. We have previously discussed grounded and ungrounded arrays. Recall that a grounded array is an array in which either the positive or the negative DC output of the array is connected to ground inside the inverter. Neither output is connected to ground anywhere else. An ungrounded array is an array in which neither the positive nor the negative DC output is connected to ground anywhere. Both grounded and ungrounded arrays require equipment grounding for safety. What we are going to discuss here applies to both grounded and ungrounded arrays. So repeating, all exposed metal parts of electrical equipment need to be connected electrically to ground. And of course, these connections need to be good electrical connections. The detailed general requirements for grounding are in NEC Article 250, which has over 100 sections. Also, additional requirements for equipment grounding in PV systems are found in NEC Section 690.41 through 690.50. In this presentation, we'll only be able to discuss some of the main points of equipment grounding in PV systems. Typical exposed metal parts in PV systems include metal frames of PV modules, metal rails for mounting, metal conduit or other metal wire supports, and the metal enclosures of components such as junction boxes, combiner boxes, inverters, and meter sockets. These components may be located inside or outside. Here are some pictures of wires in PV systems. If an energized wire becomes loose or the insulation is damaged, it may come into electrical contact with nearby metal. This contact is most likely to be with parts that enclose or support the wire, as seen in these pictures. If the metal part is not connected to ground, the wire will energize the part so that someone touching it could be injured. Other accidents can also cause ungrounded metal parts to become energized. There are no loose or damaged wires in these photographs. When such a problem is found, people rarely stop to take pictures. This figure shows that if a hot or energized wire comes into contact with an ungrounded metal enclosure, somebody touching it may get an electrical shock. However, if the enclosure is properly connected to ground, as shown here on the right, the current from the enclosure to ground causes a circuit breaker to open. This turns off the circuit before someone comes near. At the bottoms of the pictures, we see that an electrical connection to the ground is made through a grounding rod, which is a long metal rod implanted into the earth. The NEC uses the more formal term grounding electrode. A wire from exposed metal parts to ground is called an equipment grounding conductor. This is sometimes abbreviated EGC. In PV systems, equipment grounding conductors are connected to the metal frames and rails in the array. They continue with the power wires through the combiner boxes, switches, and other equipment, and in each component, the equipment grounding conductor contacts electrical connection to all metal parts. Eventually, the equipment grounding conductors from the array are connected to a grounding junction in the inverter. When the inverter is connected to an electrical panel, the link includes a grounding wire that connects the grounding junctions in the inverter and the panel. Through these connections, all of the equipment grounding conductors are connected to the electrical panel's ground, and from there to the grounding rod. There may also be a direct connection between the array or inverter and a grounding rod, as we'll soon discuss. In this diagram, an equipment grounding conductor begins by connecting to all exposed metal parts in an array. The equipment grounding conductor may have several branches within the array. The conductor continues with the power wires through the DC disconnect to the inverter, where it is connected to another equipment grounding conductor which goes with the AC wires through various parts to the grounding junction in the electrical panel. There are many challenges to proper equipment grounding in a PV system. In the array, most rails and frames are anodized aluminum. This means that the metal has a relatively non-conductive layer on the surface. This surface is insulating enough to prevent a good electrical connection with a simple contact. However, the surface is not insulating enough to protect someone who touches it from an electrical shock. And in addition, a contact between aluminum and copper wire causes galvanic corrosion, which prevents a good electrical contact. So how do we tackle this problem? First, to make a good electrical contact to anodized aluminum, you need to penetrate the anodized surface to connect to the metal below. Second, if you need a connection between aluminum and copper, you can use stainless steel between them. Stainless steel can contact both aluminum and copper without galvanic corrosion. Tin plating is also used as an intermediary between aluminum and copper. This is the older way of connecting the frames of a module to ground. We see the aluminum frame of a PV module here, and the copper equipment grounding conductor here. To connect the two, we have a stainless steel lug. You can't see it, but the lug has ridges on the bottom, so that it digs into the aluminum and penetrates the non-conducting surface. The copper wire is positioned so that it is never in direct contact with the aluminum. The aluminum rails that support the modules also need to be connected to an equipment grounding conductor. It looks like there is a little corrosion here on the copper wire. What may have happened is that the wire was originally connected with an aluminum lug that was bolted using the hole below the corroded spot. Then, when the corrosion was discovered, the old lug was replaced by the one we see now. The uninsulated copper grounding wire is allowed to be exposed here. However, such exposed wire is required to be at least size 6 AWG. The exposed metal parts of many PV systems are connected to ground as shown in this picture. However, there are several problems with doing equipment grounding as shown here. The problems include that it is very time-consuming to run all of these ground wires all over the array, and it is difficult to do so correctly. The most common mistake found in PV systems is improper equipment grounding. Lastly, the copper wires are unsightly if they are visible. You can do your best to keep the wires under the modules or someplace else out of sight, but they're usually visible someplace. If you talk to any PV system inspector, he will have a collection of pictures of grounding mistakes. Here are a few. At the top, we see an improper connection between an equipment grounding conductor and the aluminum frame of a module. It looks like this installer simply took a bolt and washer, which are not intended for a ground connection, and used them to connect the frame and the wire. At the bottom left, we see a lug that was intended for indoor use, which corroded outside on a PV array. At the bottom right, we see corrosion that contact with the copper wire caused in an aluminum frame. There are at least two mistakes here. First, you can't simply use normal bolts and washers for a grounding connection. You need to use equipment that is listed for grounding connections. Second, we see that the copper comes into direct contact with the aluminum, which will eventually cause galvanic corrosion. In this case, the wire stays above contact with the metal roof below it, but someone working on the roof could easily trip on it. This grounding lug is listed for only having one wire connected to it, but it has two. Remember, it is a code violation to use equipment in a way other than what the manufacturer intended. In this picture, we see two places where a connector intended for 2 wires is being used for 3 wires. With all of these problems and potential for errors, people started to wonder how we can do it better. People started to think, why not use the aluminum mounting rails as grounding wire? After all, they're metal, they're thick, and they already are in contact with the aluminum frames. However, both the rails and frames are anodized aluminum. This means that they both have non-conductive surfaces covering the conductive metallic interior. This led to the development of the washer electrical equipment bond, or weeb connector. Weeb connectors come in many variations to work with different types of mounting rails, but they all look something like the one shown in slide from a manufacturer's presentation. It's a very thin stainless steel washer that goes in between an aluminum module frame and an aluminum mounting rail where they touch each other. It has teeth on the top and bottom so that when the module frame is bolted securely to the rail, the teeth dig into both the frame and the rail. The teeth dig beyond the non-conducting surfaces on the top and bottom and make an electrical contact with the conductive metal beyond the surface. When weeb connectors came out, the manufacturers claimed that the ground connections were as good as the traditional ones using copper wire, but not everyone was convinced. However, the weeb connectors are much easier to use and less prone to problems like the ones we saw in the pictures. So they have become quite popular. It is important, however, to be familiar with both types of grounding. Conventional grounding with copper wire running to each module is found on older and some new PV systems. These pictures show some types and uses of weeb connectors. At the top, the small holes are the teeth that dig into the aluminum to penetrate the non-conducting surface. On the bottom right, we see a weeb connector between an aluminum module frame and a mounting structure underneath it. On the bottom left, we see a weeb connector making a connection between a rail and a lug. Weeb connectors between rails and module frames connect the rails and frames to each other electrically, but they still need to be connected to ground. So at some point, you need to connect one or more of the rails to a copper wire. In the configuration shown here, a copper wire will pass through the slot on the left of the lug and make a connection with ground for everything that is connected to the rail. This picture shows the teeth marks that a weeb connector makes in a piece of aluminum. Because the teeth dig in this way, you are not supposed to use a weeb connector more than once. If, for some reason, you need to remove a PV module, you are supposed to use a new weeb connector when you return or replace the module. Here is the statement that rails by different manufacturers actually have 10 to 20 times the conductivity of the 6 AWG copper grounding wire commonly used for conventional grounding. The conductivity is different for the rails made by manufacturers ProSolar and DPW. But of course, there are also disadvantages of weeb connectors, which do not appear in the manufacturer's information. These include that weeb connectors need to be different shapes to work with different types of rails. They can't be used at all for some types of rails, although by now, weebs are so popular that there is not a great market for rails that they can't be used with. Weeb connectors can be difficult to position. They need to be in just the right place to be squeezed between a module frame and a rail. Once a weeb connector is installed, it is difficult to know if it is positioned properly or even there at all. So if a grounding problem is detected, it can be difficult to figure out where the bad or missing connection is located. In addition, electrical inspectors like to see that the grounding is done properly, especially since they know to look for bad grounding. They may not be happy with grounding connections in places where they can't be seen during an inspection. Some inspectors have not permitted them. And as we've mentioned before, weeb connectors should only be used once. This means that you need to install new ones when replacing a module. Other ideas are also being developed by some manufacturers. One is to get rid of the metal frame entirely. If you don't have an electrically conductive frame, you don't need to ground it. Frameless modules are common for thin film modules. However, they are rare for the silicone wafer modules that are being used in most residential and commercial scale PV systems. Another option is to make modules with hard plastic frames. These can be non-conductive but still quite strong. These have been developed, but they are very rare and none may be on the market at present. Overall, modules with non-conductive frames or no frames at all have been surprisingly low to catch on. After all, it's much easier not to have to deal with connecting aluminum frames to ground. So why do most silicone PV modules still have aluminum frames? One reason is that many of the early designers of PV modules were interested in applications on satellites. They were used to using aluminum, and strong, reliable structures are essential in space. More recently, the market has become dominated by lower-cost PV modules from new Chinese companies. To get a foothold in the market, new companies want to make products that are easily interchangeable with products that are already on the market. Someone who has already designed an array based on one company's modules might consider lower-cost modules from a different company if the design doesn't need to be done again. In fact, large projects often have modules from more than one manufacturer. Sometimes, the design is simply done for a general type of module, and then the manufacturer is chosen at the last minute depending on which modules are available and cheapest. As a result, any new company needs to model their products closely on what is already being sold. This means using aluminum modules like most other manufacturers. It's kind of a herd mentality, but this is what is happening. But some change may be coming. Trina Solar, a major Chinese PV module manufacturer, announced the new frameless silicone wafer module on February 4, 2013. No spec sheet or official photographs are yet available on the company's website, but these pictures were taken at a trade show on February 6, 2013. The modules have silicone wafer solar cells between two pieces of heat-treated glass and are sealed around the edges. These pictures show the front and back of a thin film module by First Solar. These and similar products have been on the market for several years. The thin film solar cells are deposited on one piece of glass, and then another piece of glass is placed over it and a laminate is applied to seal the glass plates together. Depending on the design, the thin film may be on the underside of the top piece of glass, or the top side of the bottom piece. Non-metallic racking has also been developed by a few manufacturers. This rack is made up of fiberglass, except for the metal clamps to hold the PV modules in place. This rack is intended for a flat roof. We are not aware of any non-metallic racking for sloped roofs, except for products which integrate solar cells into a roofing product. But getting back to more common systems, in most systems, especially residential and commercial scale systems, we have metallic frames and rails that are required to be connected to ground in the inverter. This means that all of the equipment grounding conductors we saw for modules and rails lead first to the inverter ground. The inverter ground is then connected through the equipment ground to the grounding bus in the electrical panel. This connection also grounds the cases of other components it passes through. Ground wire must run with the power wires. In addition to this normal grounding, which is what one would find for any exposed electrical equipment, the NEC also wants an additional connection to ground for the equipment on the DC side of the system. This requirement can be somewhat confusing because it has been different in different versions of the NEC. The simplest requirement was up through the 2005 NEC. In this case, the NEC simply required an additional grounding wire going from the inverter directly to the grounding rod, but this was changed in most recent versions of the NEC. Let's look at this in an illustration of a PV system. Let's start with the string of modules in an array. We'll add a second string here. We'll bring the positive and negative outputs from the first string to this junction box, and from the second string to this junction box. Next, we'll combine the outputs of these two strings in the combiner box here. We'll wire from the combiner box to a DC disconnect, and from there to an inverter. This is a grounded system, so in the inverter we have a GF5 fuse to ground from the negative output of the array. On the AC side of the inverter, we have an output meter and an AC disconnect. From there, the power goes to the electrical panel of the building. As we've seen in many systems, the combiner box, the DC disconnect, and the inverter are in the same enclosure. Now we'll connect the frames of our first string of modules to an equipment grounding conductor. If we are using weave connectors, then part of the equipment grounding conductor is a rail. If not, the rail also needs to be connected to the equipment grounding conductor. Either way, the frames and rails need to be connected to a grounding wire that heads into the junction box. We also need to do the same connections between the rails and frames of the second string and an equipment grounding conductor going into the second junction box. From the junction boxes, the equipment grounding conductors go to the combiner box, where they can merge and then onto the DC disconnect and the inverter. If the enclosures of the combiner box and the DC disconnect are metal, then they need to be connected to the equipment grounding conductor, as shown here. We refer to the ground and the DC part of the PV system as the DC ground. On the AC side of the system, the equipment grounding conductor goes from the inverter through the other components into the electrical panel. Since the enclosures of the inverter and the other components are almost always metal, these enclosures also need a connection to the equipment grounding conductor. The equipment grounding conductor is connected to a grounding bus in the electrical panel, and the bus is connected to a grounding rod. The equipment grounding conductor on the AC side of the PV system is called the AC ground. The AC and DC grounds are connected to each other in the inverter, which is also where the power from the array is converted from DC to AC. The NEC through the 2005 edition required a wire from the connection point of the DC and AC grounds directly to a grounding rod. You could install a separate grounding rod, or you could make a direct connection to the grounding rod used by the electrical panel. It was usually easier to connect to the electrical panel's grounding rod. However, this was not very feasible in some PV systems. Suppose you had an array on the roof of a large building, and you put your inverter on the roof or on an upper floor of the building. It is often difficult or impossible to run a new grounding wire from an inverter on or near the roof to the building's grounding rod somewhere in the basement. Depending on your interpretation of the 2005 NEC, it may also have been acceptable to make a connection between a grounding rod and the DC ground somewhere at the array. In the 2008 version of the NEC, a direct connection is specified between the DC ground and a grounding rod, as close as possible to the array. This makes sense for a ground-mounted array away from the building, but is less practical for an array on a roof. If the array is on a roof, it is unclear whether the requirement is met with a direct wire to a grounding rod from where the DC and AC grounds meet in the inverter. If it is acceptable, a connection to the building's existing ground might also do. Both of these are subject to interpretation. With this lack of clarity, much of the requirement depends on the decision of the local electrical inspector. Finally, the 2011 NEC gave several alternatives for grounding. One option is a connection to a grounding rod at the array. This is a good choice if the array is on the ground and separated a little from the building. The direct connection to a grounding rod can also be from the point in the inverter where the DC and AC grounds meet. This is the requirement from the 2005 NEC and earlier versions. The NEC also allows this connection to be an existing ground also used by the electrical panel. Lastly, if nothing else is feasible, you are allowed to use the AC equipment grounding conductor to the electrical panel as your only grounding connection. However, this AC equipment grounding conductor has to be unspliced. This means that it has to be a single continuous wire with no screw or twist connections along the way. Permanent crimps and soldered connections are permitted. We show here the 2008 NEC grounding requirements. You may wish to stop the video to read them. This spells out the grounding requirements in the 2011 NEC for you to read. In summary, let's go over the key points on equipment grounding. First and foremost, all exposed metal parts of electrical equipment must be electrically connected to ground. This is for the safety of people who might touch the metal. Wires and other conductors that make electrical connections to ground are called equipment grounding conductors. There are many detailed requirements for these conductors and the connectors that make the links to ground. We could only touch briefly on these. In PV systems, metal PV module frames and rails must be grounded. This presents some unique challenges and some interesting solutions. The most common methods are copper wire connected to every frame and rail with an appropriate lug or weave connectors. The NEC also wants PV systems to have an extra grounding connection. This requirement has been different in different versions of the NEC, and future changes are likely.